Hello students and welcome to the course on CS 301 Systems 4. Before beginning the course, let's go through the objectives of this course. Since this is the fourth course in the collection on systems, as we've already been studying Systems 1, Systems 2 and System 3 in the earlier semesters. So the main objective of this course would be fundamentally to develop concurrent programs and then extending it further to develop certain distributed programs. The syllabus extends into 4 units. Unit 1 talks about the overview of concurrency control. Where we'll be introducing the asset properties of the transactions and other concurrency control mechanisms. Unit 2, we actually start the concurrent programming using Python, as Python is one of the most popular programming languages out there. And for good reason, the language comes with numerous libraries and frameworks that facilitates high computing, whether it be software development or web development, data analysis, or machine learning. So to begin initially with concurrent programs, we shall be using Python as a programming language and then extending it further to Erlang programming language. So our main focus would be on Erlang programming language. Unit 3, we will be introducing the concept of software transactional memory and some details of STM. Unit 4 talks about distributed computations, where we will be mainly focusing on the message passing model, the consensus problem, the mutual exclusion in distributed systems, along with the problems of atomic commit, two-phase commit, and three-phase commit problems. Here is a list of various reference books and research papers along which are prescribed in the syllabus of this particular course. There are certain snapshots of the textbook titles which can be helpful for you to go through this course. So let's begin with the unit 1, which talks about the overview of concurrency control. So the field of computer programming has enjoyed popularity since the early days of computer science. In olden days, the maximum amount of work per CPU cycle that a computer could perform was determined by the clock speed. As processor designs became more compact, physical constraints started becoming limiting factors for higher clock speeds. Consequentially, chip manufacturers started adding additional processor cores on the chips in order to increase the total performance of the system. By increasing the number of cores, a single chip could execute more CPU instructions per cycle without increasing its. There's just one problem. How can we take advantage of these extra cores? The main purpose of these multi-core systems is to provide simultaneous execution of 2 or more parts of a program to utilize all available CPU time. However, in the early 2000s, a paradigm shift in the processor business took place, and instead of making increasingly big and fast processors for computer manufacturers, they started focusing on smaller, slower processors which were put together in groups. This was when computers started to have multi-core processors. Nowadays, an average computer has more than one core. So, if a programmer writes all their programs to be non-concurrent in any way, they will find that their programs utilize only one core or one thread to process the data, while the rest of the CPU sits idle doing nothing. This is the reason for the recent push in concurrent programming. Another reason for the increasing popularity of concurrency is the growing field of graphical, multimedia, and web-based application development, in which the application of concurrency is widely used to solve complex and meaningful problems. For example, concurrency is a major player in web development. Each new request made by a user typically comes in as its own process or asynchronously coordinated with other requests. If any of those requests need to access a shared resource, Where data can be changed, concurrency should be taken into consideration. Considering the present day, with an explosive growth of data over the internet, for every second, concurrency is more important than ever. The current use of concurrent programming emphasizes correctness, performance, and robustness. Some concurrent systems, such as operating systems or database management systems, are generally designed to operate indefinitely, including automatic recovery from failure and not terminate unexpectedly. Concurrent programming is quite ubiquitous in the field of software development. Computing systems model the world, and the world contains actors that execute independently of but communicate with each other. In modeling the world, many parallel executions have to be composed and coordinated, and that's where the study of concurrency comes in. The concept of concurrency has been around for quite some time. The idea was developed from early work on railroads and telegraphy in the 19th and early 20th centuries. Concurrency was first applied to address the question of how to handle multiple trains on the same railroad system in order to avoid collisions and maximize efficiency, and how to handle multiple transmissions over a given set of wires in early telegraphy. Concurrency is the notion of multiple things at the same time. This is generally achieved via time slicing or truly in parallel if multiple CPU cores are available to host the operating system. We have all experienced a lack of concurrency, most likely in the form of an app freezing up when running a heavy task. UI freezes doesn't necessarily occur due to the absence of concurrency. They could just be symptoms of a buggy software, but the software that does not take advantage of all computational power at its disposal is going to create these freezes when it needs to do something resource intensive. This is the dictionary definition of concurrency, which means simultaneous occurrence. So a concurrent program is one defining actions that may be performed simultaneously. So in Python, the things that are occurring simultaneously are called as tasks, or they can be called as threads or a process. But at a high level, they all refer to a sequence of instructions that run in order. Let's consider some real-life examples of concurrency. Our brain and mind are wonderful examples of concurrency. Your daily routines that we do are a very good example of multitasking. The railway networks, the machines in the factory, the banking systems, the travel and reservation system, multiplayer games, well-coordinated teams are awesome real-life examples of concurrency. The hardware examples of concurrent systems include a single processor that can have multiple execution pipelines, a processor having multiple cores, a computer having multiple processors, a network that can have multiple computers, an internet having multiple networks, and all combinations of the above are hardware examples of concurrency. Following a few software examples where concurrency is present. So concurrency plays an important role in most programming languages like C++, Erlang, Go, Ruby, Scala, Python, and so on. Again, since almost every computer today has more than one core in its CPU, desktop applications need to be able to take advantage of that computing power in order to provide truly well-designed software. Majority of the smartphones today have a dual-core CPU. So, mobile development also has to stay connected to concurrent applications. As far as the video games are concerned, two of the biggest players on the current market are the PUBG and Xbox 360, which essentially use the power of multi-core systems. It is estimated that on average, Google processes over 40,000 search queries every second, which equates to over 3.5 billion searches per day and 1.2 trillion searches per year worldwide. So apart from having massive machines with incredible processing power, concurrency is the best way to handle massive amount of data requests. A large percentage of today's data and applications are stored in the cloud. Since computing instances on the cloud are relatively small in size, almost every web application is therefore forced to be concurrent, processing different small jobs simultaneously. As it gains more customers and has to process more requests, a well-designed web application can simply utilize more servers while keeping the same logic that corresponds to the property of robustness that was mentioned earlier. Even in the increasingly popular fields of artificial intelligence and data science, major advances have been made in part due to the availability of high-end graphics card, that is the GPUs, which are used as parallel computing engines. In this day and age, computer or internet users expect instant output. No matter what applications they are using, and developers often find themselves struggling with the problem of providing better speed for their applications. So in terms of usage, concurrency will continue to be one of the main players in the field of programming, providing unique and innovative solutions to those problems. As mentioned earlier, whether it be video game design, mobile apps, desktop software, or web application development, concurrency is and will be omnipresent in the near future. So to summarize, we can see that there are a lot of programs which run concurrently. For example, downloading file, listening to streaming audio or a movie, having a clock running, chatting, analyzing data from experiments, printing something, running a simulation, typing a text editor are all examples, software examples of concurrency. High volume servers, multiple clients are serviced at the same time, possibly in parallel or in an interleaved execution manner to give the appearance of responsiveness. Pipes are another command line examples of concurrency. Many algorithms, sorting algorithms like merge sort, quick sort, operating on independent slices of an array, computing primes are all software examples of concurrency. Now in this example on the slide, we see that the tasks can run concurrently but not in parallel. So this is similar to having multiple conversations in chat room and interleaving between them, but never truly conversing with two people at the same time. So this is what we call concurrency. It is the illusion of multiple things happening at the same time when in reality they are switching very quickly. So concurrency is about dealing with lots of things at the same time. Contrast this with parallelism model in which both tasks run simultaneously. Both execution models exhibit multi-threading, which is the involvement of multiple threads working towards a common goal. Multi-threading is a generalized technique for introducing a combination of concurrency and parallelism into your programs. This talks about the difference between the sequential versus concurrent versus parallel programming. So in case of sequential programming, each individual task is serviced by the CPU. And when that task is completed, the next task can be given the CPU time. In concurrent programming, you have two lines of tasks and they are executed in an interleaved fashion by a single CPU. Finally, come to parallel processing, where we have processes in two queues and each task has been serviced independently by the different CPUs. This is another example of concurrent program. We have 5 threads running in parallel, and we see that the threads are overlapping they have overlapping lifetimes. So what do you mean by overlapping lifetimes? If you look at thread 1 gets executed at one particular time. It is exempted, thread 2 starts executing. Thread 2 does not complete fully and thread 3 starts executing and so on. So after thread 5 completes its execution, thread 1 resumes its execution again and then finally completes it. So during lifetime of thread 1, we see that thread 2, thread 3, thread 4 and thread 5 also have occurred. This means that these threads 2, 3, 4 and 5 are overlapping with lifetime of thread 1. So this is a very good example of concurrency. Another example of concurrency in life example is the fast food chain, where there is order and collection. So if it is a concurrent system, we see that there is a person to serve both the counters, order and collect. Whereas in system, you have two persons serving at the order and the collection counter. Again, another example on concurrency, you see that when it is a concurrent system, you have two queues and one poke machine, and the two queues are executed in an interleaved manner with a single poke machine. Whereas in a parallel system, you have two different poke machines and two different queues are being serviced using these independent poke machines. In case of parallel systems, you have two CPUs and the tasks are executed independently on two different CPUs. And in concurrent systems, you have task 1, task 2, and task 3 executed in an interleaved fashion by a single CPU or a single processor. And finally, we'll be talking about what distributed systems or what are distributed computing does and how the distributed computing or programs that can be written in Python or in Erlang programming. So we will be learning different algorithms using distributed computing systems. And that's all for today's introductory session on Systems 4 lecture, where we talked about the overview of concurrency control mechanisms and different examples, real life examples, software examples, and hard examples on concurrency. Thank you for watching.